in this section, we're going to take a look at the common ion effect in relation to bases and their salts. So we can also observe the common ion effect with respect to weak bases. We talked in the first section about weak acids. Consider the ionization of ammonia, NH3 in water, which produces NH4 plus and OH minus. If we add a salt that contains the ammonium ion to the ammonia solution, Le Chatelier's principle predicts that the equilibrium will shift to the left. In this case, if we add the salt, ammonium chloride, NH4Cl, it would add more ammonium ions to the solution, shift the equilibrium to the left toward the reactants, and in that case, the NH4 plus is the common ion. All right, let's look at example 3 in the presentation for the common ion effect. Compare the pH of a 0.45 molar solution of ammonia and another solution of 0.45 molar ammonia and 0.15 molar ammonium chloride. Kb for ammonia is 1.8 times 10 to the minus 5. So in 3 steps, first we'll calculate just the pH of the ammonia only solution. Then the pH of the ammonia solution with the common ion in the ammonium chloride. And then we'll compare the pH values and explain the observation with respect to Le Chatelier's principle. All right, let's calculate the pH of just 0.45 molar NH3. Start by writing the dissociation of NH3 in water to NH4 plus and OH minus. Initially, we have just our reactant, just NH3, 0.45 molar, and no product. We're going to use the variable X to show the dissociation of the NH3. So we're going to decrease our concentration of NH3 by an amount X, and in doing so, increase both OH minus and NH4 plus an amount X. So that at equilibrium, here are our concentrations, 0.45 minus X, and then X for both OH minus and NH4. All right, so once we know the concentrations at equilibrium, we can use the Kb expression to find our unknown X. So Kb, which was given as 1.8 times 10 to the minus 5, is the concentration of the products at equilibrium over the concentration of the reactants. For NH4 plus and OH minus, I can substitute X from my ICE chart, and I get X squared. Now for the concentration of NH3, I just have 0.45. Now, we had said at equilibrium that the concentration was 0.45 minus X, but this change, the dissociation is not very big, right? And so given by this small Kb value. So this change relative to the initial concentration is very, very small. We can assume that it's close enough to 0 that at equilibrium, the concentration is approximately 0.45, or the same as its initial concentration. So that's why you have that there. We solve for X and we get 2.85 times 10 to the minus third. Now, what does X represent? It represents the concentration of the ammonium and the hydroxide, which we can use to find the POH, the minus log of hydroxide ion concentration. I get 2.55. And to answer the question, I need to just solve for the pH. I get 11.45. All right, so now in part B, let's calculate the pH of a solution of 0.45 molar NH3. So we're starting with the same solution of NH3, but now we're adding 0.15 molar NH4Cl. So I still have the same dissociation equation and the same Kb for the base NH3. I start with my same 0.45 molar NH3, but the initial NH4 plus is not 0, this highlighted cell. In part A, this was 0. It's 0.15 molar NH4 plus from this addition here. And it's important to note that the change is still minus X or plus X, so that at equilibrium we have 0.45 minus X for NH3, X for OH minus, and 0.15 plus X for the NH4 plus. However, the 0.15 molar NH4 plus is almost entirely from the NH4 salt, not from the ionization of the weak base NH3. The NH3 and OH minus concentrations are about the same as their initial concentrations since X is negligible. So what that means is this change is so small that we can assume X is so small relative to the initial concentration that we can ignore it. We're not going to ignore it here, right? Because that's the only change. And it's going to help us determine the pH. But when you have it here and here relative to a large initial concentration, it's so small that it's almost negligible and we can ignore it. All right, so we can use the same KB and KB expression from part A, but just substitute the different concentrations at equilibrium. So OH minus, I have these backwards, but OH minus is X, NH4 is 0.15, and NH3 is 0.45. Rearrange to solve for X and we get 5.4 times 10 to the minus 5 molar, keeping in mind that that X represents the hydroxide ion concentration. So we can find the POH, 4.27, and from there, the pH, 9.73. All right, finally in part C, let's compare the values in parts A and B. So A is just the NH3, B is the NH3 plus the ammonium chloride. And explain with respect to Le Chatelier's principle. So in part B, the addition of this salt results in additional NH4 plus, which will shift the equilibrium to the left toward the reactants and away from the products. That means the products will decrease, including the hydroxide ion concentration, which will result in an increase in the POH and a decrease in the pH, which you see here. All right, example 4. Compare the pH of a solution of 0.050 molar pyridine, C5H5N, and another solution that contains the 0.075 molar pyridine and a 0.085 molar solution of pyridinium chloride, which is C5H5NHCl. Kb for pyridine is given as 1.7 times 10 to the minus 9. So we're going to calculate the pH first of the pyridine on its own, then the pyridine with the pyridinium chloride, and then we're going to compare with respect to Le Chatelier's principle. And I want to show you, this is pyridine, C5H5N, and pyridinium chloride, C5H5NHCl. This is similar to ammonium, if this was NH3, and ammonium chloride. All right, so I've written down the dissociation equation for the weak base, pyridine, in water. We get C5H5NH plus and hydroxide. We initially start with 0.0750 molar pyridine and no products. The variable X is the amount of dissociation of the pyridine, so we're going to decrease by X. It's equal to the increase of both products so that our equilibrium concentrations are given, as you see here. Just keep in mind, X is very small relative to the initial concentration here. And so it's small enough that when we do our calculation in the next slide, we'll ignore that minus X. All right, so once we know the equilibrium concentrations, we can write a Kb expression. This is products over reactants, and then substitute our equilibrium concentration. So both of our products, we have X, so X squared over the reactant concentration, 0.0750. Set it equal to our Kb, and rearrange to solve for X, we get 1.13 times 10 to the minus 5 molar. Now what's important is, what does this X represent? It represents our two products, the most important of which is the hydroxide ion, which we can use to find the POH, and then the pH, 9.05. All right, so in part B, we still have our 0.0750 molar pyridine, but the initial C5H5NH plus concentration is not 0, as it was in part A. Now it's 0.0850. And that initial concentration comes almost entirely from the addition of that pyridinium chloride, meaning it's not coming from the dissociation of the pyridine. Of course, we have our change as this pyridine does dissociate some into OH and C5H5NH plus for our equilibrium concentrations. Now remember, this change with respect to the initial concentration is very, very small. So the concentration of C5H5N and C5H5NH plus stay about the same as their initial concentrations, since X is negligible compared to the initial concentration. So we'll see that we can ignore that in our calculations in the next slide. Okay, so Kb, which is given as 1.7 times 10 to the minus 9, is the concentration of the products in the dissociation over the reactants. And then I just substituted the values at equilibrium from the previous slide. Solve for X, and I get 1.5 times 10 to the minus 9. X being the hydroxide ion concentration. So we can find the POH and therefore the pH, 5.18. All right, now finally in part C, let's compare the pH values in part A, where it's just pyridine, and part B, where we have pyridine and pyridinium chloride. Adding the pyridinium ions here, the addition of pyridinium ions shifts the equilibrium toward the reactants away from the products, which results in a decrease in the hydroxide ion concentration, which you can see here. Big decrease there, right? 10 to the minus 3 to 10 to the minus 9. A decrease in the hydroxide ion concentration increases the POH and decreases the pH, which you can see reflected in the table.